So good morning, good afternoon, and good evening, guys, based on the time zones you all are coming from. So guys, before we start with the session, can you all please give me a quick information if you all can see my screen and hear me loud and clear as well? Great. Thank you for the information, everyone. So my name is Neeraj Kedia, and I have been working in this IT industry for more than 13 years now. So before we get started, let me quickly introduce you all to Edureka Masterclass community as well. So this community of masterclasses was started back in 2019, and since then we have been closing into more than 32,000 members so far. And in these masterclasses, we have been conducting multiple webinars and live events on different topics, including blockchain, IoT, artificial intelligence, machine learning, big data, and multiple front-end and back-end development technologies. Here, we are going to start our discussion on SVM, as in support vector machine. How exactly this is structured and how exactly this is going to be helpful for us. So first of all, we are going to talk about what exactly is machine learning to have a quick clarity on that. And then we are going to talk about what exactly is support vector machine. And then we'll talk about how exactly it works. And then we'll talk about the SVM kernels. And then we are going to talk about the components of that process of implementation of SVM as a part of a discussion. And if time allows, then we can also see a small hands-on on top of it as well. All right. So first of all, if we talk about machine learning itself, so what exactly is machine learning? So machine learning is simply making sure that we are going to automate the entire system by using a good amount of data set, right? So we can say machine learning is simply the process of feeding a machine enough data to train and predict a possible outcome using the algorithms which we have the access to. So basically, if we use more data set, then we can increase the accuracy of the results. And let's say you may have used multiple predictions made in support before any major match, right? So in this case, let's take an example for a football penalty session. So the data of previous performances are going to be considered. So let's say the goalkeeper has saved all the penalties to his right in the last 50 penalties he has saved. Now this data will be crucial to predicting if he or will save or he will not save the next penalty faces. So there are other factors to consider as well. And another example can be the suggestion that we get while surfing the internet. So the data of our previous choices are processed to give us the most favorable content we are most likely to watch. Anyhow, machine learning is just feeding the machine an ample amount of data. There goes a lot of processes, algorithms, and decisive factors to get the optimum results. All right, so here basically we have three main types of machine learning as well, where we have supervised, unsupervised, and then we have reinforcement learning. So supervised in simple terms is train me. It works on a simple training. We have to train the model, then only it can work. And then unsupervised learning is I'm self-sufficient in learning based on their own learning. We are simply going to allow them to have, again, to allow them to have the access as well. So that is what we are going to define for both. So based on their own understanding, they are going to work accordingly. That's how it's going to work. And then we are going to work on reinforcement learning. So reinforcement learning is simply learning on its own based on the feedback. We simply let the system know okay, if they have done a good job or not. And based on that only, they simply try to get the best possible output. That's how it works. All right. So in supervised learning, we use multiple labeled data set to train the system. And under unsupervised learning, we use unlabeled data set. So the data is sometimes unlabeled or we can say uncategorized, and the machine makes the best possible reference and predictions without any supervision. And then we have reinforcement learning. So reinforcement learning simply ensures that okay, we are simply going to train the system based on the feedback. So the machine needs to establish a systematic pattern of approach in reinforcement learning here. So that's how we discuss. Again, here we have supervised. Again, under supervised, we have multiple models. Like we have regression, decision tree, we have reinforcement models. We have different models currently available. Whereas in under unsupervised, we have multiple models. Like we have clustering, we have association analysis, we have hidden Markov model. So again, the KNN trees, logistic regression, naive Bayes, and SVM, they all are types of classification. Where if we talk about the a priori, FV growth, K-means, PCA, SVD, they all are part of unsupervised. And again, reinforcement is simply based on its own structure that we are going to discuss as we proceed further step by step. All right, so now next is we are going to discuss on what exactly we mean by support vector machine. So a support vector machine was first introduced in the 1960s and later improvised in 1990s as well. And it is basically a supervised learning machine classification algorithm that has become extremely popular nowadays because of its, you can say, efficient results, and especially for the complicated scenarios it can deliver it for us as a part of support vector machine. Now, as you can see here, simply it is like a discriminative classifier that is formally designed by a separative hyperplane itself. And SVM is implemented in a slightly different way than the other machine learning algorithms. So it is capable of performing classification, regression, and outlier detection as well. And support vector machine is basically, again, simply designed by as a separative hyperplane itself, as we discussed. So basically here we can have multiple data pointers that can be mapped so that the points of different categories are going to be separated by a gap. And in addition, so basically SVM can also perform non-linear classification. So we'll be talking more about the how exactly support vector machine works as we proceed further, but there are multiple advantages of using SVM as well. For example, it is effective in high dimensional spaces. It is effective in cases where the number of dimensions is greater than the number of samples. And it is, again, it simply uses a subset of trading points in decision function that makes it memory efficient. And it has different kernel functions that can be specified for decision function that also makes it versatile. And same way, we also have multiple, we can say, downside or we can say disadvantages of using SVM as well. So the number of features is much larger than the number of samples. Then we can simply avoid overfitting and choosing kernel functions. And again, recognizing them is crucial. And SVM did not directly provide probability estimates. And these are calculated using the five-fold cross validation. And how does SVM work? So the main objective of a support vector machine is to segregate their given data in the best possible way. And when the segregation is done, the distance between nearest point is known as the margin. And the approach is set to a basically hyperplane with the maximum possible margin in the support vector, as we can see here, that has been right now presented. All right. And now basically here to select the maximum hyperplane. So now in the given sets, the support vector machine follows again multiple sets. For example, is simply going to generate the hyperplane which segregates the classes in the best possible way. And then we are going to select the right hyperplane with the maximum segregation from either nearest data pointers. So basically there are different ways of or even dealing with inseparable or we can say non-linear planes as well. So for example, in some cases, hyperplanes cannot be very efficient. And in those cases, the support vector machine uses a kernel trick to transform the input into a higher dimensional space. And with this, it becomes easier to segregate the pointers. So now let's talk about the SVM kernels. So basically, SVM kernel adds more dimension to a low dimensional space to make it easier to segregate the data. It converts the inseparable problem to separable problems by adding more dimensions using the kernel trick. And a support vector machine is implemented in practice by a kernel. And the kernel trick helps to make more accurate classifier. So we can take a look at different kernels in a support vector machine. Like we have linear, we have radial based, and then we have polynomial kernels as well. First of all, let's talk about the linear kernels. So a linear kernel can be used as a normal dot product between any two given observations. So the product between the two vectors is the sum of multiplication of each pair of input values. So we can understand this. So if we talk about the linear kernel, So basically, as we discussed, linear kernel can be used as normal dot product between any two given observations. For example, here we can define this one as suppose b0, and it can be added to sum of, let's suppose, multiplied by xi. All right. So as we discussed, again here it is going to be the product between two vectors is a sum of multiplication of each pair of input values as a part of simple linear kernel equation. And then we have polynomial. So this one is for linear. Then we have for polynomial kernel. So polynomial kernel is what? Polynomial kernel is like a is rather generalized form of the linear kernel. And again, it can distinguish curved or non-linear input space. So for example, here we can refer this as suppose as k, and then we can define multiple pointers like suppose x1, x2, and then we can simply add this to a plus. Now here we have defined suppose x1, and again, although the going to be defined here x1t, and then x1 for, again it is a value for x2 here for x2, and again the entire one has to be raised to power b itself. So next, after polynomial we are going to have, we also have radial space. So here after polynomial we have the radial basis function kernel. So in terms of radial basis function kernel, so here the radial basis function kernel is commonly used in the SVM classification, and it can map the space in infinite dimensions. So basically, if we talk about the actual dimensions here, so here we can represent it as suppose the value of kx1, and again for x2, and here we can find the exponent where exponent is going to be suppose for minus 4, again the gamma value, and let's say we represent this as y, and then we can define this for x1 minus this is going to be x2, and then it has to be raised to power 2. So basically x1 minus x2 is simply going to be the Euclidean distance between the x1 and x2. So we can say x1 minus x2 is Euclidean distance, is the Euclidean distance between x1 and x2 here. And where if we talk about here, if we talk about the current component for b, so here we can say b is what? B is the degree of kernel, in case you don't have, in case you don't have the knowledge of it yet. And then a is going to be, or we can say a is what? A is the constant term. A is the constant term that we have. So here we have linear, polynomial, and then we have radial basis function. So there are multiple use cases. So before we proceed further, so there are multiple use cases of this radial base I can say component as well. So here we can use it for the phase detection, for text and hypertext categorization. Here we use it for the classification of images, for bioinformatics, for protein fold, and remote homology detection as well. We can use it for different use cases. And we can also use for, again, having a prediction control as well, as we discussed in SVM. So there are multiple use cases for face detection, for bioinformatics, for text and hypertext categorization, for remote homology. So these are different use cases that are currently available here. So now in terms of how to implement SVM, so first of all, we have to load the data, we have to explore the data, we have to split the data, and then we also have to generate the model, and then we have to evaluate the model as well. As we had discussed, again, in case you have been confused, so linear is simply going to be the dot product between any two given observation itself. And here we define here the product is going to be between two different vectors. It's simply going to be the sum of multiplication of each pair. And then under polynomial, so basically here we can distinguish curved or non-linear input space, where we have defined the k1 as x1, x2 for where a is simply going to be a constant term, and b the power to which we have increased it. So B is simply going to be the degree of kernel that we are going to make use of. And then under radial basis, as we discussed, it is commonly used in classification and can map the space in infinite dimensions as well, where x1 minus x2 is simply going to be the Euclidean distance. We can say this one that we define here, x1 minus x2 here is simply going to be the Euclidean distance here. All right, so let's do one thing. Let's open up PyCharm community here. So we can start by simple loading the data set and then working on top of it. So we can use any ID, we can use any Python ID to get started. We can use anything. So let's do one thing. Let's create a new project. Let's say we name it as SVM. So in case you don't have the access to SVM as of now, so you can go ahead and download the community version. So this is going to give you the access to PyCharm, or we can use any other ID as well if required. All right, so here, once we are in the project here, we can simply go ahead and create a new file altogether. So let's name it as our demo file. So first of all, we are going to work from the sklearn library. So here we can use from sklearn. We are going to import the data set. So there are some sample data sets available under sklearn library itself. So here we can define the cancer data set already available under sklearn. And here we can use datasets dot load, and then we are simply going to load support for breast cancer. We can load this current dataset already available. And now if we want to simply print the current dataset that we have currently imported, so here we can define cancer data dot data, and again we only want to print the 5 first rows available in that. So here we can define these statements here. So we are going to use a sample dataset currently available, and whenever we are going to work on any project, in case they are now in case the dataset is not available, then we can go ahead and simply install more libraries by simply choosing the current dataset, and then here we can go ahead and click on add, and from here we can search for any library that may be missing. For example, here we are going to work on sklearn, so we have to make sure that we do import sklearn, because without sklearn library we will not be able to work on the SVM here. So here we are simply going to work on the sample dataset. All right, so as you can see now, sklearn has been installed. So again, this is a package that we're going to work with. So here we can close it. If we want to work on the other components, we can search for any library and then we can have it installed. All right. So now we can click on apply. And then once we now, if we don't have the library installed, and then if we try to run this up, it is simply going to throw us an error. And as you can see currently, this is going to update the package, and then from there it is simply going to load the breast cancer dataset, which is available as an inbuilt sample in sklearn. So it is simply going to get connected to the server, and then from there it is simply going to pull the breast cancer dataset, and then it is simply going to print the first 5 rows from that dataset. So it may take a while depending upon which dataset we have imported. So before we perform any calculation, let me just show you how exactly this looks like. Again, in the meantime, this is getting pulled here, so we can simply go ahead and create a new file. It has been timed out because of memory error. Okay, we misspelled data. It has to be data itself, then only it is simply going to fetch the data from there. So as you can see here, now we have the first 5 rows in terms of this breast cancer data, which has been pulled automatically from sklearn, as you can see here, right? So now we are going to, here we have defined the data set, right? So now if we are going to simply split the data, right? So we are simply going to divide the data into training set and the test set to get accurate results. And after this, we will split the data using the train test split function. So here we are going to need 3 parameters, like in the sample that we are going to see. So from here, we are going to load the current data set. So for example, now just to avoid confusion for you all, so we can create a new file. Let's say we define some as suppose demo2. So here we can define from sklearn. So first of all, we define from sklearn library, from sklearn dot model, and here we can define model selection. So here we are going to import train test split. As we discussed, we are going to split it, and then we can define from cancer data that we are going to import. So here we are going to find data set dot load breast cancer, which is already available. And then we are simply going to define the models in terms of, suppose here we define X train, and then we can define X split, we can define for X test, and then we can define same thing for Y train, for Y test. X train, X test, Y train, Y test. So here we are going to define this from the same train test split that we are going to import, and then here we are going to divide them under from the cancer data and the data which has been imported here, and then we are going to define this for cancer data target. So say here we can define this for cancer data dot target, and then we can define the test size. Here we can define the test size. Suppose we want to keep the test size, suppose as 4, this test size as 4, and then we can define random state. We can define random state as suppose 109, anything that we want to have. So here we are simply going to split the data set with the given in the X train, X test, and the Y train and Y test here. So here the entire data set is simply going to be split. So as you can see, now we have split the entire data set. So now we are going to generate the model as well. So what we can do, so now here we are going to we can say generate the model, and for that we can import another library. For example, here we can import, let's say, sklearn, and here from sklearn we are going to import the SVM. So here we are going to create the library. So here we could create a classifier here. So first of all, we can define classifier as suppose svm dot svc, and here we can define the kernel. Here we can define the kernel as suppose linear, whatever we want to use we can define that, and then we are going to train the model. So we can say we are simply going to now train model. So here we have create classifier, and now we are going to train the model. So for train the model we can define class dot fit, and then we can define this value as X train that we have already imported, and then we can define for Y train that we have already performed the split on, and then simply we are going to have a prediction done. So here we can define predict response, and for getting the response we can define prediction as class dot predict, and for this we are going to make use of X test that we have already defined. We define for X train and for Y train, and then for prediction we are simply going to do that on the text, on the X underscore test data that we already have defined. That depends upon type of data that we have. So that totally depends upon the type of data we are going to simply import. And let's move this import from top here. So here we define this in the top section from sklearn. We are simply going to import the SVM that we had defined. All right, and then we had defined the classifier. Now we are going to evaluate the model, and for evaluating the model, we can simply go ahead and define. So here from sklearn, we can also import other components as well. From sklearn, we are also going to import metrics. So here we are also going to import metric, and by using we can say metric for getting the accuracy, we can define for getting the accuracy. We are going to define, we are simply going to print the accuracy of the prediction here, and for accuracy we are simply going to define metrics, which is again available under the metrics library. Here we have accuracy score, and then from here we are simply going to find Y test, and we are going to find this one for Y prediction as well that we have defined. So I think we have used Y test, we have used uppercase for we have used, let's do one thing, let's use small case for everything just to avoid confusion. Let's define this as test, train, and test again. So you have a y test, and then you define here we define it for prediction, and then for finding the precision score, for finding precision, we can simply print another statement as precision score. And in here, we can again make use of metrics. And for metrics, we can define the precision score itself. So here we can define precision underscore score. And in here, for precision score, we are going to make use of y test. And then we are going to make use of y prediction. All right. And then at the end, if we are simply going to recall the score and we are simply going to report. So here we can define for recall, we can print another statement. For recall, we can define this one as recall. And here from same metrics dot recall score. And for here, we can define y test and y prediction for the prediction that we are going to define. And then if you want to print all the metrics, so here we can define print metrics dot classification report. And for that, we are going to make use of y test and y prediction for prediction made. All right. So here we had defined these, and now once we have configured everything, so here we can simply run this up, and we would be able to see the entire output once it has been defined. So now we can see here we have the accuracy, here we have the precision score, the recall score that we had defined, and then we define the accuracy based on whatever data we are going to work on. Depending upon that, we are simply define the current data set here. Thank you so much for joining, guys, and have a great day ahead. Take care. Bye bye.